If the universe is expanding, what is it expanding into? Unlike objects in a room that move into empty space, the universe has no container, no outside to grow into. Expansion isn't galaxies moving through space, it's space itself stretching, carrying galaxies, clusters, and photons along as the cosmic fabric grows. There is no edge, no external void, and yet everything moves apart. This mind-bending idea defies everyday intuition, forcing us to rethink the very nature of space, boundaries, and the universe itself. Everyday analogy. A useful way to grasp the universe's expansion is by imagining a balloon being blown up. Picture the balloon's surface covered with tiny dots, each representing a galaxy. As the balloon inflates, the dots move away from each other, not because they are moving on their own, but because the surface itself is stretching. Importantly, the balloon doesn't require extra space around it to expand. The stretching occurs within the surface. In the same way, the universe's expansion doesn't need an outside space. It's space itself that is growing. This analogy also explains why every observer sees other galaxies moving away from them. No matter which dot you pick on the balloon's surface, all other dots appear to recede. Similarly, in our universe, every galaxy sees all others moving away, creating the illusion of a center of expansion, when in reality, there isn't one. However, like all analogies, the balloon model has its limits. The balloon's surface is two-dimensional, stretching in three-dimensional space, whereas our universe is three-dimensional and may expand in ways we cannot directly visualize. Despite these limitations, the balloon analogy provides a concrete image for the otherwise abstract concept of space itself stretching, helping us understand why there is no edge and no external space into which the universe is expanding. Defining expansion. When scientists talk about the universe expanding, they are describing something profoundly different from the way objects move through space in everyday life. It is not as if galaxies are speeding away through a static backdrop of emptiness, like cars driving on a road. Instead, the very fabric of space, the distances between galaxies, is increasing. This means that space itself is stretching, carrying galaxies along with it. Galaxies aren't necessarily moving locally through space. Their relative motion is dominated by this stretching of space on cosmic scales. This concept is central to modern cosmology and arises naturally from Einstein's theory of general relativity. According to this framework, mass and energy tell spacetime how to curve, and in turn, the geometry of spacetime determines how objects move. The expansion of the universe can be quantified by the scale factor, a number that grows over time, describing how distances between points in space increase. A galaxy 1 billion light-years away from us today will be much farther away in the distant future, not because it drove that distance, but because the space between us and it has expanded. Another way to think about it is in terms of light. Light traveling from a distant galaxy is stretched along with space, which we observe as a redshift. The longer the wavelength, the farther the galaxy has receded due to cosmic expansion. This redshift is not caused by the galaxy speeding through space, but by the stretching of space itself during the light's journey. Understanding expansion in this way is crucial because it resolves many misconceptions. If galaxies were moving through space rather than being carried by expanding space, we would expect to see different patterns in their velocities and distribution. Instead, the uniform stretching predicts the exact observations astronomers have made, galaxies receding from us in proportion to their distance, as encapsulated in Hubble's law. The Big Bang context. The story of the universe's expansion begins with the Big Bang, the event that marked the birth of space, time, matter, and energy. Around 13.8 billion years ago, all of the observable universe, every galaxy, star, planet, and particle, was compressed into an incredibly hot, dense, and infinitesimally small point known as a singularity. At this moment, there was no outside, into which the universe could expand. Rather, space itself began to stretch from this singular state. The Big Bang was not an explosion in space like a bomb going off. It was an expansion of space itself. Every part of the universe began moving away from every other part as space expanded. This is why, when we look at distant galaxies today, we see them receding from us in all directions. There is no central point from which everything is moving outward. In fact, every observer, anywhere in the universe, would see the same pattern of expansion. In the first fractions of a second, the universe underwent inflation, a period of extremely rapid expansion that stretched space by unimaginable factors. This inflation smoothed out irregularities and created the nearly uniform cosmos we observe today. Following inflation, expansion continued at a slower, steady rate, gradually forming the cosmic structures we see now: galaxies, clusters, and vast filaments of matter interwoven with dark matter. The Big Bang framework also helps us understand that expansion is inherent to space itself. It isn't a matter of galaxies moving into pre-existing space, but rather that space was created in the process and has been stretching ever since. Every increase in distance between galaxies, every observable redshift of light, is a direct consequence of this cosmic stretching that began at the moment of the Big Bang. Spacetime fabric. Einstein's theory of general relativity revolutionized our understanding of space and time by merging them into a single entity, spacetime. Rather than treating space as a static stage on which objects move, general relativity describes spacetime as a dynamic, flexible fabric that can bend, stretch, and warp in response to the presence of matter and energy. This concept provides the framework for understanding cosmic expansion. Space itself is not rigid but malleable, capable of growing without requiring an outside into which it expands. Visualizing spacetime as a flexible fabric can be helpful. Imagine a stretched rubber sheet. Placing heavy objects on it causes dips and curves, illustrating how gravity emerges from the warping of spacetime. Now, instead of dipping, picture the sheet uniformly stretching in all directions. Objects on the sheet move apart, not because they are propelling themselves, but because the underlying fabric is expanding. In the universe, galaxies are like marbles on this stretching sheet. They appear to recede from each other purely due to the expansion of the fabric itself. This model also clarifies why the universe can expand without an edge or boundary. Unlike a solid object that requires room to grow, the fabric of space-time can stretch intrinsically. It doesn't need a pre-existing void to push into. The expansion occurs within the geometry of space-time itself. This stretching influences everything from the paths of light traveling across billions of light years to the formation of cosmic structures, making the expansion a central feature of the universe rather than a movement through a surrounding space. By thinking of space-time as a flexible, stretching fabric, it becomes easier to grasp how the universe can grow on a cosmic scale, carrying galaxies along with it, without invoking a bigger space outside. Expansion is a property of space itself, embedded in the rules of the cosmos as described by Einstein. No edge concept. One of the most confounding aspects of the universe's expansion is that it doesn't seem to have an edge. Unlike ordinary objects or confined spaces, where expansion implies pushing outward towards some boundary, the universe exhibits no such limit or outer rim. Every observation we make suggests that every point in the cosmos is moving away from every other point, and this movement happens uniformly in all directions. From our vantage point on Earth, distant galaxies appear to recede in every direction, but the same observation would hold true from any galaxy elsewhere. There is no central point of expansion, no cosmic frontier, and no edge to cross. The universe isn't like a balloon being inflated into a room, where the edges of the balloon are expanding into pre-existing air. Instead, space itself grows everywhere at once, and every location experiences the same stretching effect. This property of having no edge can be difficult for the human mind to comprehend because our brains are wired to think in terms of bounded spaces. When we imagine something expanding, we picture it stretching into a larger container. The universe, however, does not conform to this intuition. It is either infinite or unbounded in a way that defies everyday analogies. If the universe is infinite, it has always been so in extent, and expansion simply means that distances within it are increasing. If it is unbounded but finite, like the surface of a 3D sphere or a higher dimensional analog, there is still no edge. Traveling far enough in one direction could eventually bring you back to your starting point, much like circumnavigating the Earth. In either case, there is no outside or external boundary that the universe is growing into, and this challenges our very notions of space and geometry. Mathematically, this idea is represented through the metric expansion of space. In cosmology, the scale factor in the Friedmann-Lemaitre-Robertson-Walker (FLRW) metric describes how distances between points in the universe change over time. According to this model, the relative positions of galaxies are not fixed in a static space. Instead, they scale proportionally with the expansion of the universe itself. This scaling applies uniformly across all points, meaning that every region of space is stretching without any preferred direction or external reference. This is why we observe the Hubble law, where the velocity at which a galaxy recedes from us is proportional to its distance. The farther away a galaxy is, the faster it appears to move, creating the appearance that all space is expanding from every vantage point. The absence of an edge also ties into the cosmic principle known as homogeneity and isotropy. On large scales, the universe is approximately uniform in composition and structure, and it appears the same in every direction. If there were an edge, this principle would break down. There would be regions where the properties of space differed dramatically from others, and the distribution of galaxies, cosmic microwave background radiation, and dark matter would not be uniform. Observational evidence from the cosmic microwave background, the afterglow of the Big Bang, supports this uniformity to a high degree of precision, confirming that the universe's expansion is not directional toward an edge, but uniform everywhere. Another way to think about the no-edge concept is through higher dimensional analogies. Consider the surface of a 2D sphere embedded in 3D space. If an ant were walking on the surface, it would never encounter a boundary. The surface is finite, yet unbounded. Now imagine a similar principle extended to 3 spatial dimensions or more. Our 3-dimensional universe could be finite yet unbounded in this higher dimensional sense, meaning that expansion increases the distances between points but does not require an external void. The outside is a misleading idea because, in a 3-dimensional, unbounded universe, there is no higher dimensional space that the universe is expanding into. Space itself is all there is, and it stretches from within. Even more strikingly, the concept of an edge fails when we consider general relativity. In Einstein's equations, the geometry of space-time is determined by the distribution of energy and matter, but the equations themselves make no assumption of an external spatial container. The universe's expansion is a property of space-time itself. The notion of an edge or boundary would imply a discontinuity in the metric of space-time, but no such discontinuity is observed. Instead, space-time is continuous and smooth on cosmic scales, meaning that there is no abrupt ending, no outer wall, and no boundary toward which the universe expands. This idea also reframes the common misconception of the universe expanding into nothing. It isn't that the universe is pushing into an empty void. Rather, every point of space stretches, and every galaxy moves away from others because the intervening distances grow. From any location, it appears as though everything else is moving away, giving the illusion that there is some center of expansion, when in reality, there is none. Every location can be thought of as the center in its own local frame of reference, yet globally, there is no edge or boundary. This fundamentally challenges human intuition and makes the expansion of the universe one of the most counterintuitive phenomena in all of physics. Even cosmic topology theories, which explore the large-scale shape of the universe, support the idea of no edge. Whether the universe is flat, positively curved, or negatively curved, the observations of large-scale structure and the cosmic microwave background radiation suggest that there is no boundary. In a flat or negatively curved universe, the cosmos could be infinite, while in a positively curved one, it would be finite but still unbounded, much like the surface of a sphere, just extended into higher dimensions. In all cases, there is no physical edge toward which the universe is expanding. The lack of an edge also has practical observational consequences. Light from distant galaxies can reach us only from within a certain range, defined by the observable universe. But this is a limit of what we can see, not a true boundary of the cosmos. Beyond this horizon, galaxies exist and space continues, but their light hasn't had enough time to reach us since the Big Bang. This gives the appearance of a boundary, but it is merely a limit of observation, not a limit of space itself. Thus, the no-edge concept is not only a theoretical requirement, but also consistent with empirical data. Observable universe limit. While the universe itself may have no edge, our observable universe does, and it is defined not by physical boundaries, but by the limits imposed by the speed of light and the age of the cosmos. Light travels at a finite speed, which means that when we look at distant objects in the universe, we are seeing them not as they are today, but as they were when the light left them millions or even billions of years ago. This introduces a natural horizon, a maximum distance from which light has had time to reach us since the Big Bang. Beyond this horizon, galaxies exist, stars shine, and cosmic structures form, but their light has not yet arrived. To us, this creates the illusion of a boundary, a sphere centered around Earth, giving the impression that the universe ends at some distance. However, this is entirely a limitation of observation, not a true edge of space. This horizon grows over time. As billions of years pass, light from increasingly distant regions finally reaches us, gradually expanding the volume of the observable universe. Yet no matter how far we see, this boundary is relative to our location. Any other galaxy would have its own observable horizon centered on itself. From the perspective of an astronomer in Andromeda, the observable universe would look very similar, but shifted in location and content. This relative horizon reinforces the idea that the universe itself has no true boundary. It simply extends beyond what we can detect at any given moment. The concept of the observable universe also has profound implications for understanding cosmic expansion. When astronomers measure the redshift of distant galaxies, they are seeing the cumulative effect of billions of years of space stretching. The farther away a galaxy is, the more its light has been stretched, and the faster it appears to be moving away from us. This creates a relationship captured in Hubble's law, which links a galaxy's recession velocity to its distance. It's important to recognize that galaxies near the edge of our observable universe are not moving faster in any intrinsic sense. Their apparent speed is a result of space itself expanding over the time the light traveled. The expansion is ongoing, and beyond our observational horizon, space continues to stretch, carrying even more distant galaxies along with it. Interestingly, some galaxies currently beyond our observable horizon will never be seen by us, because the rate of cosmic expansion exceeds the speed at which light can travel to reach Earth. This means that parts of the universe are forever inaccessible, lying outside the bounds of observation. These regions are not empty. They contain matter and energy like the regions we can see. They contribute to the universe's mass-energy content and affect its overall geometry, but remain hidden behind the cosmic horizon. This again highlights that the edge we perceive is only a horizon defined by light travel time, not a true boundary of space. Cosmologists also use the observable universe to map the distribution of matter, and dark energy. but all measurements must be interpreted in the context of this horizon. For example, the cosmic microwave background, CMB radiation, the remnant glow from the Big Bang, represents the most distant light we can detect. Observing it allows scientists to see the universe as it was about 380,000 years after its birth. Even beyond the CMB, space continues. Regions that emitted this radiation are merely the furthest that light has reached us from, not the furthest that exists. This makes the observable universe a practical tool for study, but not a representation of the universe's total extent. The finite speed of light also leads to a phenomenon known as look-back time, where distant objects are seen as they were in the past. Galaxies that appear near the edge of our observable universe are glimpses into the young universe, showing structures and conditions vastly different from those we see nearby. The ongoing expansion of space stretches their light even further, increasing their redshift and reinforcing the appearance of a distant boundary. However, this boundary is purely a consequence of observational limits. Beyond it, the universe continues to expand just as it does within our view. Thus, the observable universe demonstrates an important principle. What we can see is not all that exists. Our horizon creates a temporary edge, a limit to our perception, but not a physical end. The universe itself is likely far larger, possibly infinite, extending beyond our ability to detect it. The apparent boundary is a reminder of the interplay between the finite speed of light, the age of the cosmos, and the expansion of space, illustrating how perception and reality diverge on cosmic scales. Flat versus curved universe. Understanding the geometry of the universe is crucial for interpreting its expansion and ultimate fate. The universe may not conform to the simple three-dimensional Euclidean geometry we learn in school. Instead, cosmologists consider three possible large-scale geometries: flat, positively curved, spherical, and negatively curved, hyperbolic. Each of these geometries affects how space stretches, how light travels, and how matter is distributed, fundamentally shaping our understanding of cosmic expansion. A flat universe is one in which parallel lines remain parallel forever, and the angles of a triangle sum to exactly 180 degrees. This is the geometry most consistent with observations of the cosmic microwave background and large-scale structure. In a flat universe, the expansion occurs uniformly in all directions, and the rules of ordinary Euclidean space apply on cosmic scales. Distances between galaxies increase over time, but the overall shape of space remains consistent and predictable. Flat geometry also has implications for the ultimate fate of the universe. If the universe is precisely flat, its expansion will slow over time due to gravity, but it will never completely stop. Instead, it will approach a gradual, eternal expansion. Observations suggest that the universe is very close to flat, with a margin of error of less than 1%, largely thanks to the effects of dark energy, which accelerates expansion. A positively curved universe is analogous to the surface of a sphere. On such a cosmic sphere, parallel lines eventually converge, and the angles of a triangle add up to more than 180 degrees. If the universe were positively curved, it would be finite but unbounded, meaning you could travel indefinitely without ever encountering a boundary, similar to walking around the Earth. In this scenario, the expansion of space still occurs, but the curvature affects how distances scale over time. Light traveling across large distances would follow curved paths, and distant galaxies could appear closer than they really are in Euclidean terms. A positively curved universe has historically been associated with a possible Big Crunch scenario, where gravitational attraction might eventually overcome expansion and cause the universe to collapse back into a dense state, though current observations of accelerating expansion due to dark energy make this outcome unlikely. In contrast, a negatively curved universe has a hyperbolic or saddle-shaped geometry. Here, Parallel lines diverge over distance, and the angles of a triangle sum to less than 180 degrees. This type of geometry implies an infinite, open universe, where space continues outward indefinitely. In a hyperbolic universe, expansion stretches space even faster over large distances, making galaxies recede at seemingly accelerating rates without invoking dark energy. Light paths also curve differently in a hyperbolic geometry, affecting how we interpret distances and the apparent positions of cosmic structures. Such a universe has no bounds, no edge, and distances between objects can grow dramatically, enhancing the feeling of infinite space. The geometry of the universe is tightly linked to its density. Cosmologists define a critical density, the average density of matter and energy required for the universe to be flat. If the actual density exceeds this critical value, the universe curves positively. If it is lower, the universe curves negatively. Observations from the cosmic microwave background, galaxy surveys, and gravitational lensing suggest that the universe is astonishingly close to this critical density, implying near-flat geometry. However, dark energy, which constitutes about 70% of the universe's total energy content, complicates this picture by accelerating expansion and influencing the ultimate geometry at very large scales. Understanding curvature also helps us refine our intuition about cosmic expansion. In a flat universe, expansion behaves in a straightforward, linear fashion over large distances. In a curved universe, the paths of galaxies and light are affected by curvature, creating subtle observational effects such as gravitational lensing and distortions in the cosmic microwave background. For example, in a positively curved universe, two initially parallel paths of light could eventually intersect, potentially creating multiple images of distant galaxies. In a negatively curved universe, those paths would diverge, making distant objects appear farther apart than expected. These effects are measurable and are used to estimate the universe's curvature with remarkable precision. Moreover, the flat versus curved distinction has profound implications for the concept of an edge. In a positively curved universe, the cosmos is finite, yet unbounded, eliminating the need for an edge. Traveling far enough in one direction could, in theory, bring you back to your starting point. In a negatively curved or infinite flat universe, the cosmos could extend endlessly, with no edge in sight. Expansion in any of these geometries does not require an external space to grow into. Distances simply scale according to the underlying curvature and the stretching of space itself. The inflationary model of the early universe also supports near-flat geometry. During the brief period of exponential expansion just after the Big Bang, any initial curvature would have been smoothed out, leaving the universe remarkably flat on observable scales. This helps explain why our measurements today align so closely with flatness, even if the universe might have had slight curvature initially. Inflation also created the nearly uniform distribution of galaxies and cosmic microwave background fluctuations we observe, providing a connection between early expansion, geometry, and the large-scale structure of the universe. Exploring the universe's geometry also challenges our intuition. In everyday life, we deal almost exclusively with flat Euclidean space, where concepts like distance, parallel lines, and angles are intuitive. On cosmic scales, curvature alters these relationships. Two galaxies that seem a certain distance apart in a straight line may actually be closer or farther due to the underlying curvature of space. This realization helps us understand why questions about the universe expanding into what are misleading. The geometry itself defines the distances and scaling without needing an external container or higher dimensional space. Even in curved scenarios, expansion is an intrinsic property of the universe. Whether flat, spherical, or hyperbolic, the stretching of space affects all points uniformly. Galaxies recede from one another in proportion to distance, and the absence of an edge remains true. Geometry dictates how light travels, how cosmic structures evolve, and how expansion manifests observationally, but it does not imply the existence of an external void. In essence, understanding whether the universe is flat, curved, or hyperbolic provides the mathematical and conceptual framework needed to interpret cosmic expansion and appreciate why there is no outside into which the universe grows. Analogy of a raisin bread. Another intuitive way to conceptualize the universe's expansion is through the analogy of raisin bread rising in the oven. Imagine a loaf of bread dough mixed with raisins. Before baking, the raisins are scattered throughout the dough. As the dough rises in the oven, it expands uniformly in all directions. Importantly, the raisins themselves are not actively moving through the dough. They are carried apart by the stretching of the dough around them. Similarly, in the universe, galaxies are like the raisins. They appear to move away from each other, not because they are traveling through space, but because space itself is expanding between them. This analogy captures several essential aspects of cosmic expansion. First, it illustrates uniform expansion. Just as each raisin sees all other raisins moving away, every galaxy observes other galaxies receding from it. There is no single center from which expansion radiates. Second, it demonstrates that expansion is intrinsic to the medium itself. In the bread analogy, the dough is the substance stretching. There is no empty space outside the dough that it must push into. Likewise, the universe does not expand into a pre-existing void. Space is the medium that stretches, and this stretching defines the increasing distance between cosmic objects. The raisin bread analogy also helps explain why light from distant galaxies is redshifted. As the dough stretches, the distance between raisins grows. If we imagine a wave traveling through the dough, it too would stretch along with the medium. In the universe, light traveling through expanding space is similarly stretched, increasing its wavelength and shifting it toward the red end of the spectrum. This is a direct consequence of the expansion of space itself, not the motion of galaxies through a static void. However, like all analogies, the raisin bread model has limitations. Real bread rises in a three-dimensional oven, while the surface of the universe we inhabit may involve three spatial dimensions expanding in ways we cannot directly visualize. The analogy also does not capture the effect of dark energy, which accelerates the expansion, causing distances to increase faster than the simple stretching seen in rising dough. Despite these limitations, the analogy remains powerful for conveying the fundamental concept. Galaxies recede because the space between them grows, not because they are moving through some empty container. The raisin bread analogy reinforces the idea that cosmic expansion is homogeneous and isotropic. Just as raisins are carried apart uniformly in every direction in the dough, space expands similarly on large scales, maintaining a roughly uniform distribution of galaxies. This homogeneity and isotropy are key assumptions in cosmology and underpin our models of the universe's evolution. By visualizing the universe as dough rising with embedded raisins, it becomes easier to internalize the counterintuitive notion that space itself is dynamic, stretching continuously without requiring an external void or boundary. Expanding into nothing. The question of whether the universe is expanding into nothing strikes at the very heart of our cosmic intuitions, yet it is also one of the most misleading ways to phrase the problem. In everyday language, nothing suggests an absolute void, an empty stage upon which the universe could grow. However, in the context of modern physics, nothing does not carry this intuitive meaning. Space is not merely an empty box waiting to be filled. It is an active, dynamic entity with its own properties, and the expansion of the universe is a change in these properties rather than a movement into pre-existing emptiness. When we ask whether the universe is expanding into nothing, we confront the limitations of human intuition and language, which struggle to describe a phenomenon that transcends our everyday experiences. In physics, space is a flexible framework described by the equations of general relativity. It is not nothing in the metaphysical sense. It has measurable qualities, such as curvature, the ability to stretch, and the capacity to carry energy in forms such as dark energy and vacuum fluctuations. The term vacuum in physics, for example, does not signify absolute emptiness. Quantum field theory reveals that even the vacuum is seething with ephemeral particles that pop in and out of existence and with intrinsic energy, known as vacuum energy. This energy influences the expansion of the universe through its contribution to the cosmological constant, which accelerates the stretching of space. Therefore, what might appear to be nothing is, in fact, a highly structured and energetic medium. Moreover, considering expansion as a movement into nothing misrepresents the fundamental nature of the cosmos. The universe is self-contained, meaning that space itself stretches internally. When we say that the universe is expanding, we mean that distances between points in space increase over time, but these points are part of the same spatial continuum. There is no external reference point, no larger container or void into which the universe is expanding. From every observer's perspective, galaxies are receding, light is redshifting, and the cosmic web grows more diffuse over time, but this does not imply motion into an external nothingness. The very concept of outside loses meaning when applied to the universe as a whole. To grasp this concept, it helps to revisit analogies like the balloon model and the raisin bread model. In both, the outside is misleading. For a 2D balloon surface, expansion occurs on the surface itself. The surrounding 3D air is not part of the analogy for cosmic space. It is just a convenience for our imagination. In the raisin bread, the dough stretches and the raisins move apart, but the bread is the entirety of the expanding medium. Similarly, the universe does not need an external nothingness to grow. It expands internally, and space itself is the medium that carries the galaxies apart. Thinking in terms of into what or into nothing is a projection of our everyday bounded experiences onto an unbounded, higher dimensional reality that behaves fundamentally differently. The notion of nothing also intersects with philosophical and theoretical questions about the nature of the universe. If we define nothing as a state devoid of matter, energy, and even space-time, then asking what the universe expands into becomes almost nonsensical, because space-time itself was created in the Big Bang. There was no pre-existing spatial stage. The universe and space-time were generated simultaneously. Expansion is not about growing into a pre-existing void, but about the intrinsic stretching of space-time itself. Asking what is outside the universe may thus be a category error. The universe is all there is, and space itself is the arena that grows. Interestingly, this perspective dovetails with quantum cosmology and multiverse theories. Some speculative models suggest that what we perceive as nothing might in fact harbor hidden dimensions, quantum fields, or even other universes. In these frameworks, our universe could be a localized region of a larger, possibly infinite multiverse, inflating from a quantum fluctuation or bubble within a higher dimensional space. Yet even in these models, the expansion of our observable universe remains internal, and the question of what it is expanding into is reframed. It's not expanding into classical empty space, but into a context that may be beyond ordinary spatial intuition. Another consideration comes from general relativity and the mathematics of cosmology. The solutions to Einstein's field equations, particularly the Friedmann-Lemaitre-Robertson-Walker FLRW metrics, describe a universe that can expand without requiring any exterior. These solutions define the scale factor, which determines how distances between points change over time. The mathematics works perfectly well without invoking an external space. The stretching is encoded in the geometry of space-time itself. From this standpoint, the expansion of the universe is a geometric property, not a motion through an external medium. The concept of nothing is further complicated when we consider dark energy. Observations suggest that the expansion of the universe is accelerating, driven by dark energy, which permeates space uniformly. Dark energy's effects are intrinsic to space itself. It does not reside outside the universe or push against an external void. Instead, it manifests as a negative pressure that causes space to stretch faster over time. The presence of dark energy makes the question of expansion even more paradoxical. The universe is not just growing, but accelerating in its growth, and yet there is still no outside into which it grows. The expansion is entirely self-contained. Philosophically, the idea that the universe expands into nothing challenges our need for a context beyond existence. Humans naturally think in terms of surroundings, boundaries, and containers, but the universe as a whole defies these concepts. Spacetime is not a thing in space, it is the arena itself. Expansion is not motion through a medium, but a property of the medium itself. The nothing beyond is therefore not a literal vacuum, but a reflection of the limitations of our language and intuition when trying to describe a cosmos that transcends everyday experience. Even the concept of infinity plays a role. If the universe is infinite, then it cannot expand into anything because it is already unbounded. Expansion in this case is purely a matter of scale. Distances between points grow, but there is no outside edge or void. If it is finite but unbounded, like the 3D analog of a sphere, then space still stretches internally, and the notion of nothing remains irrelevant. In both cases, physics teaches us that nothing is a misleading term. The expansion is a property of space itself, not a consequence of moving into an external emptiness. Self-contained space. Many cosmologists describe the universe as fundamentally self-contained, meaning that its expansion does not require an external space or pre-existing void into which it can grow. This concept is closely related to the idea that the universe has no edge or center, and that space-time itself is dynamic and flexible. Unlike objects or fluids in our everyday experience, which expand by pushing into surrounding space, the universe expands intrinsically, with distances increasing between points as a result of the stretching of space itself. This view is one of the most important and counterintuitive aspects of modern cosmology, as it forces us to abandon the notion that growth or movement always requires an outside context. The notion of a self-contained universe arises naturally from general relativity. Einstein's field equations describe how the distribution of matter and energy determines the curvature and dynamics of spacetime. Crucially, these equations do not require spacetime to exist within a larger arena. Spacetime is all there is. The expansion of the universe is encoded in the equations themselves through the scale factor, which changes over time to describe the stretching of distances between galaxies. This intrinsic expansion does not imply that the universe is moving outward into a pre-existing void. It simply means that the metric defining distances in the universe grows, stretching the fabric of space itself. One way to conceptualize a self-contained universe is through higher dimensional analogies. Consider a two-dimensional being living on the surface of a balloon. As the balloon inflates, distances on the surface increase, and every point moves away from every other point. From the two-dimensional perspective, it appears that the universe is expanding, but there is no need for an external container for the surface itself. The surface can grow, stretch, and carry objects along without referencing any outside. Similarly, our three-dimensional universe expands in a self-contained manner. Even if higher dimensions exist, the expansion we observe is intrinsic to our three-dimensional space, and the universe does not require an external volume to push into. Observations of cosmic phenomena support the idea of a self-contained universe. The cosmic microwave background, CMB radiation, the afterglow of the Big Bang, reveals a uniform isotropic universe on large scales. The distribution of galaxies and the large-scale structure of cosmic filaments also demonstrates uniform expansion. There is no observational evidence of an edge or boundary beyond which the universe expands. In fact, every measurement we make is consistent with the idea that the universe contains all of space, matter, and energy within itself. Expansion is therefore a property of the universe, not of something growing into a pre-existing external void. The self-contained nature of the universe also resolves several conceptual paradoxes. If the universe were expanding into a larger space, we would need to explain the nature of that space. What is it made of? Does it obey physical laws? And where did it come from? By treating the universe as self-contained, cosmologists avoid these questions. The expansion is simply a change in the geometry of space-time, occurring everywhere simultaneously and uniformly. Every galaxy, every cluster, and every region of space experiences the same expansion, and there is no outside reference point. In this sense, the universe is like an infinite canvas that stretches internally, with its own geometry defining all distances and motions. The concept of self-contained space also ties into the role of dark energy. Dark energy, which drives the accelerated expansion of the universe, is not something external being applied to the universe. It is a property of space itself. It permeates all of space uniformly, exerting a negative pressure that causes distances to increase over time. Its effects are intrinsic to the self-contained universe and provide a natural mechanism for the ongoing acceleration of expansion without invoking an external force or medium. Dark energy demonstrates that the expansion is a property of the cosmos, arising from the characteristics of space-time itself. Even more profoundly, the self-contained universe reframes questions about the origin and destiny of the cosmos. In classical intuition, growth implies a pre-existing container or an external space into which an object can move. But in the context of a self-contained universe, the Big Bang is not an explosion into empty space. It is the creation of space itself. Space and time, matter and energy, all emerged from the singularity. Expansion has been occurring ever since, not into anything external, but as a scaling of the intrinsic distances defined by the very fabric of the universe. This perspective dissolves the question of what is the universe expanding into, in favor of understanding the expansion as an internal process. Distances grow because space itself stretches. The self-contained model also aligns with the cosmological principle, which states that the universe is homogeneous and isotropic on large scales. Every region of space behaves the same as every other, and expansion occurs everywhere simultaneously. There is no preferred location or direction. This reinforces the idea that the universe does not expand into something else. It expands within itself. From the perspective of any observer, galaxies recede, light redshifts, and cosmic distances increase. Yet there is no external reference frame required to define this motion. Philosophically, a self-contained universe challenges our deepest intuitions. Human thought is shaped by experiences within bounded, three-dimensional space, where objects have edges and growth requires surroundings. The cosmos, by contrast, is fundamentally different. Expansion is an intrinsic property of space-time, independent of any external stage. Thinking in terms of self-contained space allows physicists and cosmologists to model the universe mathematically, make precise predictions about its evolution, and interpret observations without resorting to ill-defined concepts like outside or nothing. Moreover, a self-contained universe provides a coherent framework for the multiverse hypothesis, bubble cosmology, and higher dimensional theories. Even if our universe exists within a larger multiverse, the observed expansion we measure is internal, governed by the stretching of our local space-time. We do not require knowledge of what lies beyond to understand the dynamics within our universe. This intrinsic self-containment makes the universe both complete in itself and consistent with the laws of physics as we know them. In summary, the idea of a self-contained universe is a cornerstone of modern cosmology. Expansion is not a motion into an external void. It is the stretching of space-time itself, occurring uniformly throughout the cosmos. This perspective resolves conceptual paradoxes, aligns with observations such as the cosmic microwave background and large-scale structure, and provides a framework for understanding phenomena like dark energy and accelerating expansion. The universe is self-sufficient, dynamic, and complete, carrying its own expansion intrinsically without requiring an outside container. Multiverse speculation. While the mainstream cosmological model treats our universe as self-contained, some speculative theories suggest that it could be part of a much larger multiverse, a grander framework in which countless universes exist alongside ours. The concept of a multiverse arises from several theoretical motivations, including the implications of inflationary cosmology, quantum mechanics, and string theory. In this speculative context, one could imagine that our universe, vast, expanding, and seemingly self-contained, is actually a single bubble in an immense cosmic foam, where each bubble represents a separate, self-contained universe. The intriguing idea here is that while our universe is internally self-contained and expanding intrinsically, it could simultaneously be embedded within a larger ensemble of universes, each with potentially different physical constants, dimensions, and properties. The inflationary multiverse model is one of the primary frameworks suggesting a multiverse. In the early moments after the Big Bang, the universe underwent a period of rapid exponential expansion, known as cosmic inflation. Some models of inflation predict that this process does not occur uniformly or terminate everywhere at once. Instead, pockets of space can stop inflating at different times, forming bubble universes, while surrounding regions continue inflating. Each bubble could have its own distinct laws of physics, matter distribution, and even dimensionality. In this scenario, our universe's expansion could be seen as occurring within a bubble that is itself part of a far larger inflating background. From our perspective, the expansion appears self-contained, but the multiverse framework suggests an even larger context in which these bubbles float and grow. String theory further provides fertile ground for multiverse speculation. According to some interpretations, the universe might consist of multiple dimensions beyond the familiar 3 of space and 1 of time. These extra dimensions could harbor other universes, each with its own configuration of space-time and physical laws. In this picture, our 3-dimensional universe could be expanding like a 3-dimensional brain embedded in a higher dimensional space, called the bulk. The expansion of our universe might then involve motion or stretching within this higher dimensional framework, although all observable effects, galaxy redshifts, cosmic microwave background fluctuations, and large-scale structure, remain determined by the dynamics internal to our bubble universe. Even if higher dimensions exist, we remain confined to our own universe, unable to detect or interact with other bubbles directly. Quantum mechanics introduces another angle on multiverse speculation. In the many worlds interpretation, every quantum event creates branching universes in which each possible outcome occurs. While these universes do not physically expand into each other in the traditional sense, they suggest a staggering proliferation of reality at scales far beyond our observation. The idea of expansion into a multiverse here is less about spatial growth and more about the proliferation of alternate realities. Yet the concept reinforces a central theme. Our universe may be only one instance among an inconceivably vast ensemble, challenging the notion of universality and uniqueness. Cosmologists often stress that multiverse speculation, while mathematically motivated and intriguing, remains unverified and untestable with current technology. No observational evidence has directly confirmed the existence of other universes, and their hypothetical properties are largely derived from theoretical models rather than empirical data. Nonetheless, the multiverse framework offers a fascinating lens through which to interpret cosmic expansion. If our universe is a bubble within a larger multiverse, its self-contained expansion does not preclude it from being part of a more extensive structure, adding a layer of complexity to the seemingly simple question of what is the universe expanding into. In this view, the expansion remains internal to our bubble, but the bubble itself exists within a larger cosmological context where other bubbles may be forming, colliding, or inflating independently. Another speculative idea within multiverse theory is the bubble collision hypothesis. If multiple bubble universes exist, their boundaries could, in principle, interact. Collisions between bubbles might leave imprints on the cosmic microwave background, creating subtle irregularities that could, hypothetically, be detectable. While no definitive evidence of such collisions has been observed, the possibility illustrates how multiverse speculation could intersect with observable phenomena, even if indirectly. In this scenario, expansion is not merely a local feature, but part of a dynamic environment in which multiple universes coexist, each with its own internal stretching of space-time. The multiverse perspective also reframes the role of cosmic inflation and dark energy. Inflation naturally produces a fractal-like structure of space in which universes continuously emerge in different regions. Dark energy, responsible for accelerating the expansion of our universe, might similarly play a role in the dynamics of the broader multiverse, affecting how bubbles grow and interact within higher dimensional space. Although speculative, this perspective provides a conceptual framework where the idea of expanding into something is not completely meaningless. It could mean expanding within a higher dimensional multiverse or inflating alongside other universes in a larger cosmic foam. Despite the allure of these ideas, it is critical to emphasize that from the perspective of an observer within our universe, expansion appears self-contained and uniform. All measurable phenomena, the recession of galaxies, the redshift of light, the stretching of the cosmic microwave background, are explained entirely by intrinsic expansion. The multiverse, if it exists, adds a layer of context that we may never directly observe. In other words, our universe's expansion does not require an external medium. It is self-contained, even if our bubble exists within a grander multiverse. The multiverse idea is speculative, but offers a tantalizing possibility. What seems self-contained from within may be embedded in something much larger, beyond the reach of current observation and comprehension. Ultimately, multiverse speculation challenges the way we conceptualize cosmic expansion. It suggests that inside and outside may not be absolute concepts, that our universe may be only one of countless others, and that its expansion is a local property of a bubble within a far larger, largely inaccessible cosmic structure. Even if the multiverse exists, the question, what is the universe expanding into, still has a precise answer for observers inside our bubble. Space-time itself is stretching, distances grow, and the expansion is intrinsic to our universe. The multiverse simply provides a broader stage on which this expansion occurs, without violating the self-contained nature of our observable cosmos. Bubble Universe Hypothesis. The Bubble Universe Hypothesis is a particularly vivid and influential idea within cosmology, suggesting that our universe may be just one bubble among countless others, each forming and inflating within a larger cosmic environment. This concept is closely tied to inflationary theory, which posits that in the first fractions of a second after the Big Bang, space underwent an extraordinary exponential expansion. While inflation ended in our local region, creating the universe we observe today, it may continue elsewhere, producing other bubble universes simultaneously or sequentially. Each bubble could have its own distinct physical properties, constants, and even dimensions, effectively making each one a separate universe in a vast multiversal network. To imagine this, picture a vast cosmic froth, with countless bubbles forming, inflating, and sometimes colliding. Each bubble is self-contained. It expands internally. Its galaxies move apart as space stretches, and local physical laws govern its evolution. Our universe is one such bubble, and its expansion is intrinsic. It stretches space within the bubble itself, rather than pushing into some external emptiness. The bubble analogy also helps clarify why observers inside any given universe perceive expansion as uniform and isotropic. From inside our bubble, all other galaxies recede in proportion to distance, as if the universe had no center or edge, because the expansion occurs throughout the bubble's interior. The bubble universe hypothesis is mathematically grounded in models of eternal inflation, an extension of standard inflationary theory. In these models, the inflationary field does not decay uniformly. While inflation ceases in localized regions, producing discrete bubble universes, other regions continue inflating, creating new bubbles over time. This process can go on indefinitely, resulting in a fractal-like multiverse where bubbles form, grow, and occasionally interact. From our vantage point, we can only observe our own bubble, and the dynamics of other bubbles remain entirely beyond detection. This reinforces the idea that the expansion we measure is internal, self-contained, and governed by the stretching of space-time within our bubble, rather than by the influence of a surrounding medium. The bubble hypothesis also helps address the cosmological fine-tuning problem. Physical constants in our universe, such as the strength of gravity, the speed of light, and the ratio of dark matter to normal matter, appear exquisitely calibrated to allow the existence of stars, planets, and life. In a multiverse of countless bubbles, each with its own physical constants, it becomes statistically plausible that at least some bubbles, like ours, possess conditions conducive to life. Our universe may be one of the rare habitable bubbles, expanding internally while coexisting with a vast, unseen ensemble of other universes. Collisions between bubble universes are another speculative but fascinating aspect of the hypothesis. If two bubbles form close enough to each other in the inflating background, their edges might collide, creating detectable imprints in the cosmic microwave background, CMB, or other large-scale cosmic structures. These interactions could appear as slight anomalies or asymmetries in the CMB, providing a potential observational window into the bubble multiverse, though no definitive evidence has yet been found. Even without collisions, the concept emphasizes that our universe is embedded within a larger context. Our expansion is internal, but it exists alongside countless other independently inflating bubbles. Interestingly, the bubble universe hypothesis aligns well with the notion of a self-contained universe. Each bubble, including ours, has its own internal expansion, governed by the properties of space-time and dark energy within that bubble. Observers inside a bubble cannot perceive the space between bubbles directly. They only experience expansion as a stretching of distances within their own universe. From this perspective, the idea of the universe expanding into something becomes nuanced. The expansion we observe is internal and intrinsic, but if bubbles exist within a larger inflating environment, they are metaphorically floating in a higher dimensional landscape. This higher dimensional space is not necessarily directly observable or physically analogous to the everyday nothing we imagine. It is a mathematical framework describing the dynamics of bubble formation and inflation. The bubble universe concept also resonates with higher dimensional cosmology, such as brane world scenarios in string theory. In these models, each bubble could be envisioned as a three-dimensional brane embedded in a higher dimensional bulk. Expansion occurs on the brane, stretching distances between galaxies, while the bulk provides the larger context in which multiple branes, bubbles, exist. This idea reinforces the notion that cosmic expansion is internal. Distances grow within the brane, not by moving into some ordinary, familiar external space. The bulk is more like a mathematical scaffolding than a classical empty space into which the universe pushes. From an observational standpoint, the bubble universe hypothesis is challenging to test. We cannot directly see other bubbles, and any influence they might have on our universe is subtle at best. Most of our understanding comes from theoretical models rooted in inflation, quantum field theory, and string theory. Yet even without direct evidence, the hypothesis provides a framework for considering how universes could exist in a grander ensemble while maintaining the self-contained expansion we observe. It allows cosmologists to reconcile the apparent uniformity and internal dynamics of our universe with the possibility of a vastly more complex and populated multiverse. Philosophically, the bubble universe hypothesis expands our perspective. While our intuition struggles with a universe that stretches without an edge or center, the idea of multiple self-contained bubbles floating in an inflating higher dimensional space offers a conceptual scaffold to understand these counterintuitive phenomena. It reframes cosmic expansion. We no longer ask, what is the universe expanding into, in terms of classical space, but consider expansion as a local property of our bubble, possibly embedded in a grander, largely inaccessible cosmic structure. Each bubble grows internally, distances stretch, galaxies recede, and light redshifts, all without requiring an external container. Our universe is simultaneously unique and self-contained, while the multiverse framework provides a broader conceptual backdrop, dimensions beyond ours. The concept of higher dimensions offers one of the most mind-bending ways to think about the universe's expansion. While humans perceive the universe as three spatial dimensions, length, width, and height, plus time as the fourth dimension, modern physics, particularly string theory and brain cosmology, posits the existence of additional spatial dimensions that are hidden from direct observation. These extra dimensions could profoundly alter how we understand cosmic expansion, suggesting that our three-dimensional universe might be embedded in a larger, multidimensional space. In this framework, when we talk about the universe expanding, it might not just be stretching internally in familiar directions, but could also be interacting with or inflating into dimensions beyond our perception. String theory, for instance, requires up to 10 or 11 dimensions for its mathematical consistency. In these models, the extra dimensions are often compactified, curled up at scales so small that they are effectively invisible to current experiments. Our observable universe exists on a three-dimensional brane, a term derived from membrane, embedded in a higher dimensional bulk. Expansion within our universe corresponds to the stretching of space along our familiar three dimensions, while the higher dimensions may provide a vast, unseen stage on which multiple branes or universes could exist. This framework allows cosmologists to imagine our universe as expanding internally while coexisting in a multidimensional environment, where the familiar concept of outside is no longer restricted to three dimensions, but can include unseen, extra-dimensional directions. Brane-world cosmology introduces even more intriguing possibilities. If our universe is a three-dimensional brane, then the expansion we observe, galaxies moving apart, light redshifting, space stretching, is confined to our brane, yet the brane itself could be moving or inflating within a higher dimensional bulk. Other branes could exist in this bulk, each with its own internal expansion, creating a multiverse in higher dimensional space. From the perspective of an observer inside a single brane, the expansion appears self-contained, uniform, and isotropic. However, the existence of extra dimensions provides a theoretical context into which the brane, and by extension, our universe, exists, though these dimensions are largely inaccessible and may not behave like conventional space. Higher dimensional theories also provide a novel interpretation of cosmic inflation. In standard inflation, space expands exponentially due to the dynamics of a scalar field called the inflaton. In higher dimensional models, inflation could involve motion or stretching, not just within our three familiar dimensions, but also along extra-dimensional axes. This offers a mechanism for bubble universes forming in different regions of the higher dimensional bulk, each with its own physical constants and laws. Our universe could be just one such bubble, expanding internally within the brane while existing as part of a more extensive, multidimensional framework. The presence of extra dimensions also impacts our understanding of gravity and dark energy. In brane-world scenarios, gravity may propagate into the higher dimensional bulk, which could explain why it is so much weaker than other fundamental forces. Dark energy, responsible for the accelerated expansion of the universe, might similarly arise from interactions between our brain and the extra-dimensional bulk. These ideas suggest that the universe's expansion, while observed as an internal stretching of space, might be influenced by dynamics beyond our perceptible 3 dimensions. One of the most fascinating implications of higher dimensional theories is that they allow a new interpretation of the universe's apparent self-containment. Even if extra dimensions exist, the expansion we observe remains local to our 3-dimensional brain. Galaxies recede, light stretches, and distances grow within our familiar dimensions. The unseen extra dimensions provide a broader backdrop, but do not constitute an external space in the classical sense. The universe is still self-contained, in the sense that all observable phenomena are governed by the stretching of space within the brain. The higher dimensional bulk simply offers a mathematical and conceptual environment in which such self-contained universes can exist. From an observational standpoint, evidence for extra dimensions remains elusive. Experiments at particle colliders, gravitational wave detectors, and cosmological observations have yet to detect direct signatures of higher dimensions. Nonetheless, the idea remains theoretically appealing because it provides a coherent framework for integrating quantum mechanics, general relativity, and the large-scale structure of the universe. It also offers a fresh perspective on the seemingly paradoxical question of what is the universe expanding into? In higher dimensional models, the expansion is intrinsic to our brain, but the brain itself exists within a larger, multidimensional space. Thus, our expansion is real, measurable, and internal, while the higher dimensions provide a broader conceptual stage without contradicting the self-contained nature of observable space. Higher dimensional theories also inspire philosophical reflections. Human intuition is grounded in 3-dimensional experience, so imagining additional dimensions challenges the very way we conceptualize space, boundaries, and expansion. We are trained to think linearly, to conceive of objects moving within a fixed stage. Yet in higher dimensional cosmology, space itself, our 3-dimensional brain, can stretch, inflate, and carry matter along, independent of any classical outside. The higher dimensions serve as a reminder that our everyday notions of edges, voids, and external space may be irrelevant when applied to the universe at large. In summary, higher dimensional theories suggest that our 3-dimensional universe may be embedded within a far more complex, multi-dimensional reality. Expansion occurs internally along familiar spatial dimensions, but the broader higher dimensional framework provides a conceptual and mathematical backdrop in which multiple universes could coexist, inflate, or interact. The dynamics of the bulk, the existence of additional brains, and the role of higher dimensional fields all influence our understanding of cosmic evolution. While unobservable directly, these extra dimensions offer a theoretical resolution to the question of what the universe is expanding into. The expansion is intrinsic, self-contained, and occurs within our brain, while the higher dimensions provide context without requiring a classical void or container. Dark energy's role. One of the most profound discoveries in modern cosmology is that the universe's expansion is not only ongoing, but accelerating, and this acceleration is attributed to a mysterious entity known as dark energy. First observed in the late 1990s through measurements of distant Type Ia supernovae, dark energy appears to constitute roughly 68% of the total energy content of the universe, vastly outweighing ordinary matter and dark matter combined. Its discovery revolutionized our understanding of cosmic expansion and added a new layer of complexity to the question of what is the universe expanding into? Since dark energy is not a force acting from outside the universe, but an intrinsic property of space itself, it challenges conventional intuitions and makes the expansion even more enigmatic. Dark energy is often modeled as a cosmological constant in Einstein's equations of general relativity. This constant represents a uniform energy density that fills space, producing a negative pressure that counteracts the gravitational pull of matter. Unlike ordinary matter or radiation, which decelerates expansion through gravity, dark energy accelerates the stretching of space, causing galaxies to recede from one another at increasing rates over time. Importantly, this acceleration does not require any external void or container. The driving force is inherent to the very fabric of space-time. Distances grow faster not because space is pushing outward into a larger arena, but because space itself possesses energy that propels its own expansion. The presence of dark energy also reframes the question of what the universe is expanding into. In a universe dominated by matter and radiation, one might imagine expansion as a gradual stretching with a decelerating rate, almost giving the illusion of a boundary forming at the edges of observable space. However, dark energy ensures that the expansion is exponential on cosmological timescales. This implies that regions of the universe beyond our observable horizon will recede so rapidly that they effectively vanish from causal contact. In other words, the universe will expand internally at such a pace that distant galaxies will eventually move beyond our ability to observe them, creating the impression of an expanding universe into an infinite, inaccessible beyond. Yet fundamentally, no external space is required. Dark energy is intrinsic, and expansion remains an internal stretching of the cosmos. From a theoretical standpoint, dark energy remains enigmatic. While the cosmological constant is the simplest explanation, alternative models, such as quintessence, propose that dark energy could be a dynamic field that evolves over time. Some speculative theories even suggest interactions between dark energy and higher dimensional space or other bubble universes, potentially linking dark energy to the multiverse or higher dimensional frameworks. Regardless of its exact nature, the key point is that dark energy is not external. It resides within the universe itself and drives expansion from within. This intrinsic origin fundamentally alters the question of what is the universe expanding into, because the expansion is self-propelled by the energy content of space itself, rather than a push into pre-existing emptiness. The observable consequences of dark energy are profound. As the universe accelerates, the distances between faraway galaxies increase faster than the speed of light relative to one another, not because they are moving through space faster than light, a violation of relativity, but because space itself is expanding. Light emitted from extremely distant galaxies may never reach us, effectively creating a cosmic horizon. This leads to a counterintuitive realization. The universe is not just expanding, it is accelerating away from itself in ways that can make regions of space forever inaccessible. The expansion is both self-contained and inexorably driven outward, a direct manifestation of dark energy's pervasive influence. Dark energy also amplifies philosophical and conceptual questions about cosmic boundaries. In a universe without dark energy, the question of what is it expanding into might be answered by simply acknowledging the intrinsic expansion of space. However, with an accelerating expansion, the universe seems to pull away from itself faster and faster, creating regions that are increasingly isolated. The question of an outside becomes even less meaningful because the observable universe is shrinking relative to the overall scale of expansion. The edge is not moving outward into pre-existing space, but the interior itself is stretching so rapidly that vast volumes become inaccessible. Dark energy makes expansion a more profound and mysterious phenomenon, one that is entirely internal, yet exhibits effects that mimic the presence of an external void. From a mathematical perspective, dark energy enters the Friedmann equations as a constant energy density, which dominates the dynamics of the universe at large scales. In the current epoch, dark energy surpasses the influence of matter and radiation, causing accelerated expansion. Projections suggest that this acceleration will continue indefinitely, potentially leading to a cosmic future dominated by isolation, where galaxies beyond our local group recede beyond detection, and the observable universe becomes a small island in a vast, inflating space. Importantly, The acceleration does not imply motion into pre-existing space. It is simply the growth of scale within the universe itself, amplified by the intrinsic properties of dark energy. The role of dark energy also connects to other speculative cosmological frameworks. In multiverse or bubble universe models, dark energy may vary from bubble to bubble, creating universes that expand at different rates. In higher dimensional theories, dark energy may interact with the bulk, influencing the rate at which branes or bubble universes expand internally. Despite these theoretical possibilities, all observable effects of dark energy remain confined to the universe we inhabit, reinforcing the notion that cosmic expansion, even when accelerated, is self-contained and intrinsic to space-time. Ultimately, dark energy deepens the mystery of cosmic expansion. The universe stretches and accelerates internally, driven by a pervasive energy intrinsic to space itself. Galaxies recede, light redshifts, and vast regions become inaccessible, creating the illusion of an ever-expanding horizon. Yet, from a fundamental standpoint, no external space is required. Dark energy shows that the expansion of the universe is an internal phenomenon, powered from within, and the question of into what is it expanding becomes even more subtle. It is not expanding into classical nothingness or an external void. It is expanding into itself, propelled by the intrinsic energy of space-time, accelerating faster with every passing moment. Expanding inside itself. One of the most critical and conceptually challenging ideas in modern cosmology is that the universe is expanding inside itself. Contrary to intuitive thinking, the expansion does not involve galaxies or cosmic matter moving outward into an external space or pre-existing void. Instead, the distances between points in space are increasing because space itself is stretching, creating more room between galaxies without requiring any outside container. This internal expansion is a direct consequence of general relativity, where space-time is dynamic rather than static, and it fundamentally reshapes our understanding of cosmic growth. To visualize internal expansion, consider a rubber sheet analogy, but with an important twist. Instead of stretching into a surrounding room, the sheet itself grows uniformly everywhere, and all points on it move apart from each other without reference to an external frame. Every galaxy sees other galaxies receding, not because they are propelling themselves outward, but because the metric defining distances in the universe is changing. This intrinsic growth explains why the universe appears homogeneous and isotropic on large scales. No location is special, and the expansion is uniform throughout the cosmos. Every observer, regardless of position, would measure the same general behavior, galaxies receding proportionally to distance, as dictated by Hubble's law. Mathematically, this internal expansion is described using the Friedmann-Lemaitre-Robertson-Walker FLRW metric, which models the universe as a homogeneous and isotropic space. The scale factor, a function of time, quantifies how distances evolve within the universe. As the scale factor increases, all spatial separations grow proportionally. Crucially, this process requires no external space to push into. It is entirely a feature of the geometry of the universe itself. In essence, the universe does not expand into something. Rather, the concept of distance evolves, and the universe grows internally in scale. Internal expansion also resolves common misconceptions about cosmic motion. Many people intuitively imagine galaxies flying away from a central point, implying a center and an outside. Observations show no such central point exists. Instead, every location is moving away from every other location due to the stretching of space between them. This is why analogies like the raisin bread or balloon surface are so useful. Raisins or points move apart as the dough or surface expands internally, and the outside is irrelevant to the process. Internal expansion, therefore, removes the need for a boundary or external medium, aligning with the principles of general relativity and observed cosmic uniformity. The internal nature of expansion also explains the puzzling observation that some galaxies recede faster than light. This apparent superluminal motion is not a violation of relativity. Rather, it occurs because the space between galaxies is stretching, increasing the distance at a rate that exceeds the speed of light. Locally, no object moves faster than light through space. Globally, the universe's scale grows internally. This subtlety underscores how different the universe's expansion is from any everyday motion we experience, and why thinking in terms of internal stretching rather than movement through space is essential. Dark energy further emphasizes the internal nature of expansion. The acceleration caused by dark energy does not push the universe outward into an external medium. Instead, it enhances the stretching of space internally. Galaxies move apart more quickly, cosmic horizons appear, and the observable universe effectively shrinks relative to the vast, accelerating fabric of space. Expansion remains internal. The distances grow, the universe scales up, but no external void or container is involved. The universe enlarges itself, not into something, but by increasing the metric distances that define it. Conceptually, internal expansion challenges human intuition. Our brains are wired to think about space in terms of edges, boundaries, and containers. We imagine objects growing or moving into pre-existing space, but the universe does not conform to this limited framework. The cosmos expands internally, and all observable effects, the redshifting of light, the recession of galaxies, the cooling of the cosmic microwave background, are manifestations of this intrinsic stretching. There is no edge, no center, no external medium. The universe is simultaneously complete and expanding from within. Internal expansion also provides a coherent framework for understanding a potentially infinite universe. If the universe is infinite in spatial extent, expansion does not require an outside into which it grows. The internal stretching simply increases distances everywhere, scaling up the infinite space. Even in a finite universe without edges, the internal nature of expansion explains why all points recede from each other, why there is no observable boundary, and why cosmologists can model the universe as a self-contained entity whose growth is intrinsic rather than external. From a philosophical perspective, thinking of expansion as internal invites a shift in worldview. The universe is not a balloon growing into a room, nor a particle moving outward from a center. It is space itself becoming larger, carrying all galaxies, radiation, and cosmic structures along as it stretches. This internal growth transcends human intuition and challenges our natural conceptions of motion, distance, and scale. It reframes the question of what is the universe expanding into as somewhat misleading. The universe does not expand into anything. It expands itself. In summary, the concept of expansion as an internal process is fundamental to modern cosmology. Distances between galaxies increase because space itself stretches. This process is governed by the scale factor, influenced by dark energy, and consistent with observations such as the cosmic microwave background and Hubble's law. It requires no external container or void, no outside medium. The universe grows intrinsically, uniformly, and self-consistently. Internal expansion is the clearest and most accurate way to understand cosmic growth. The universe expands inside itself, and the stretching of space-time carries everything along in its vast, accelerating, and awe-inspiring evolution. The infinite universe. The notion of an infinite universe pushes our understanding of space and expansion to the very limits of human comprehension. When we think of expansion, it is natural to imagine growth within some kind of boundary or container. But if the universe is infinite, such imagery fails entirely. An infinite universe is not stretching into anything external. It is already unbounded, without edges, without limits. In this scenario, expansion does not involve the creation of more universe beyond a frontier, because every region of space already extends infinitely. Instead, expansion becomes a scaling phenomenon. a proportional stretching of distances between points within an already unbounded cosmic continuum. This idea may seem counterintuitive at first, but it aligns perfectly with the principles of general relativity and modern cosmological observations. To understand this, consider that infinite does not necessarily imply static. A universe that is infinite can still experience an expansion in which all distances between points increase over time. Each galaxy moves away from every other galaxy, not because it is traveling through a pre-existing void, but because the metric that defines distance itself is evolving. In an infinite universe, there is no special center or preferred point. Every location experiences the same relative expansion. This internal scaling preserves the symmetry and isotropy that are hallmarks of our observable cosmos. The universe grows in scale, but because it is infinite, there is never a need for an outside to accommodate that growth. Expansion becomes a feature of the geometry of space, not a motion into some external arena. Mathematically, the infinite universe is modeled using the Friedmann-Lemaitre-Robertson-Walker FLRW metric with a spatial curvature of 0, corresponding to a flat geometry. Observational evidence from the cosmic microwave background, large-scale structure, and baryon acoustic oscillations suggests that the universe is very nearly flat on large scales, which is consistent with an infinite spatial extent. In such a flat, infinite universe, the scale factor, a measure of relative distances, can increase without bound, causing all points to recede from one another while preserving the infinite nature of space. In other words, expansion is a relative growth rather than a creation of additional space beyond some limit. Every volume expands, every galaxy recedes, yet the totality of the universe remains infinite at every moment in time. One profound implication of an infinite universe is the concept of eternal existence. If space is infinite, it may have been infinite at the moment of the Big Bang as well. In this picture, the Big Bang does not describe a point exploding into empty space. Rather, it represents a hot, dense state that filled an infinite cosmos. Expansion from that state did not create space externally, but caused all regions to cool, thin, and stretch proportionally, setting the stage for galaxy formation, cosmic structure, and the evolution of the observable universe. The observable horizon, the limit imposed by the speed of light, gives us only a finite patch of this infinite reality. Beyond our observational limits lies more universe, equally vast and structured, perpetually scaling alongside our local region. In essence, we are living in a finite window of an infinite expanse, experiencing local expansion, while the universe at large remains boundless. An infinite universe also reframes many philosophical questions about cosmology. Concepts like an edge or outside lose their meaning entirely. Expansion in an infinite universe does not require a container, does not need a surrounding nothingness to push into, and does not imply the creation of additional space in a classical sense. The universe's growth is internal, proportional, and uniform everywhere. Every observer, no matter where they are, would measure the same Hubble expansion. Galaxies receding at velocities proportional to their distance, distances stretching, and light redshifting. The infinite nature of space means that these observations are independent of any boundary. There simply isn't one to measure against. The infinite universe scenario also has deep implications for cosmological probabilities and fine-tuning. If space is infinite, all configurations of matter that are physically possible may occur somewhere, even infinitely many times. This suggests that any particular arrangement of galaxies, stars, or planets is not unique, but one instance among infinitely many. Our observable universe, with its particular combination of physical constants, dark matter density, and cosmic structures, is then a localized sample of an infinitely vast and diverse cosmos. Expansion simply stretches the metric relationships within this infinite fabric. it does not alter the overall infinitude of possibilities. From a theoretical standpoint, the infinite universe also interacts with concepts like dark energy and cosmic acceleration. Even if the universe is infinite, dark energy drives the accelerated expansion of the scale factor. This causes galaxies to move away from each other faster over time, potentially faster than light relative to one another on large scales. Yet this motion does not violate relativity, because it is space itself that is stretching, not objects moving through space. In an infinite universe, acceleration amplifies internal expansion without creating an external edge or boundary. The universe expands internally, the metric grows, and vast regions of space eventually move beyond the observable horizon, but the total spatial extent remains infinite. The infinite universe perspective also helps reconcile counterintuitive aspects of cosmology. For instance, in a finite universe, one might struggle to imagine what expansion means without invoking an outside. But if space is infinite, expansion becomes an intuitive scaling process. Every small volume grows, distances between points increase, and light traveling from distant galaxies stretches along with space itself. The universe grows internally at every point, uniformly and proportionally, without any reference to an external container or boundary. Infinity eliminates the need for the classical notion of expanding into, and replaces it with the concept of ever-increasing scale within an unbounded continuum. Another remarkable implication is that an infinite universe supports the concept of internal horizons. Even though space is infinite, the observable universe is limited by the speed of light and cosmic history. Galaxies beyond our horizon are effectively unreachable and unobservable, yet they exist as part of the infinite continuum. As the universe continues to expand, more regions move beyond our horizon, yet the universe itself remains infinite. Expansion is therefore internal, uniform, and relative, without reference to external space. The idea of expanding into nothingness or an external medium becomes meaningless in this context, as infinity has no outside to grow into. Philosophically and scientifically, considering an infinite universe emphasizes a radical shift in perspective. Our intuition, honed for finite objects and bounded spaces, fails when confronted with an unbounded cosmos. Expansion is not growth into emptiness. It is the stretching of an already unbounded space, where every distance increases and the universe scales internally. From this standpoint, questions about the universe beyond its edge are nonsensical, because there is no edge. Cosmic growth becomes a dynamic process of metric expansion, intrinsic to the fabric of an infinite cosmos, revealing a universe both unimaginably vast and internally self-consistent. In conclusion, if the universe is infinite and has always been, expansion is not a matter of moving into something else. It is an intrinsic scale change. All distances increase, galaxies recede, light stretches, and cosmic structures evolve, yet the totality of space remains boundless. The universe grows internally everywhere at once, without edges, boundaries, or external containers. Observers perceive redshifts, cosmic acceleration, and recession, but these are all local manifestations of a global, unbounded scaling process. In an infinite universe, the question of what is the universe expanding into transforms into a deeper realization. The universe does not expand into anything. It expands itself, stretching endlessly within an infinite continuum, a self-contained yet unbounded cosmic fabric. Human perspective trap. One of the most intriguing obstacles to understanding the expansion of the universe is rooted not in physics, but in human cognition. Our brains evolved to navigate a world of bounded, tangible objects. Cliffs have edges, containers hold things, rooms have walls, and objects move through space. This spatial intuition is powerful and reliable for everyday life, yet it becomes a significant conceptual trap when applied to the cosmos. We instinctively imagine the universe as a three-dimensional container or a balloon inflating into some pre-existing emptiness, prompting the seemingly natural question, what is the universe expanding into? But this intuition misleads us because the universe does not conform to the constraints of everyday, three-dimensional experience. The universe's expansion is fundamentally metric and internal, not a process that requires an external spatial context. Our mental model of space imposes boundaries and edges where none exist. We conceive of an outside because all objects we interact with have one. We see a balloon inflating and instinctively associate it with the surrounding air, which seems necessary for the balloon to occupy. This reasoning, while correct in daily life, is misapplied to cosmic expansion. The universe, whether finite or infinite, is not inflating into a pre-existing void. Rather, it creates more separation between points internally as the metric-defining space evolves. Thinking in terms of a container introduces conceptual errors. It suggests a center, a direction of expansion, and an exterior, all features that are absent in a self-contained universe. Every galaxy observes the same isotropic recession pattern, illustrating that expansion has no privileged center, no edges, and no external reference frame. Another cognitive trap comes from our temporal intuition. Humans perceive time linearly, as a series of cause and effect events happening within a bounded spatial context. When we consider cosmic expansion, we instinctively think of a beginning that spreads into a pre-existing beyond. While the Big Bang represents a temporal origin of our observable universe, it was not an explosion into empty space. Rather, it was a state in which all space, already infinite or self-contained, was extremely dense and hot. Our spatial and temporal intuition cannot easily grasp this, leading to persistent misconceptions about edges and outward motion. Understanding expansion requires letting go of these ingrained notions, acknowledging that space itself changes, distances grow, and the universe evolves internally. Even analogies designed to aid understanding, like balloons or raisin bread, can reinforce cognitive biases. They are useful for illustrating internal expansion and isotropy, but they implicitly suggest that the universe is embedded in a larger context. Human cognition struggles to internalize the idea that the universe is self-contained. Our minds instinctively project the familiar logic of bounded objects onto something fundamentally unbounded. Similarly, when we contemplate higher dimensions, multiverses, or infinite universes, we face additional mental barriers. Extra dimensions cannot be visualized directly, and infinite spaces defy everyday comprehension. These challenges highlight that human perspective is a cognitive constraint, not a physical limitation of the universe itself. The trap extends to how we visualize cosmic horizons and light travel. Our intuitive sense of space makes it tempting to think that galaxies moving faster than light are breaking the rules, or that distant regions are approaching some undefined edge. In reality, superluminal recession occurs because the metric of space expands internally. It is the universe itself stretching between points. The edge, we imagine, is merely the observable horizon, determined by the finite speed of light and the finite age of the universe. Beyond it lies more universe, equally real, and yet inaccessible. This distinction between perception and reality is crucial. Cognitive biases lead us to infer boundaries where none exist. Philosophically, acknowledging the human perspective trap is essential for true comprehension. Science asks us to think beyond intuitive categories of inside, outside, center, and periphery. We must accept that our universe might operate on principles fundamentally alien to everyday experience. It can expand without a boundary, grow without an outside, and stretch without a container. Internal expansion, infinite or finite space, higher dimensions, and dark energy all defy our ingrained spatial heuristics. Conceptual clarity requires decoupling human intuition from cosmic reality, embracing abstraction, and relying on mathematical frameworks like general relativity to guide understanding. This trap also illustrates why cosmology is both fascinating and challenging. Observational data, cosmic microwave background radiation, galaxy surveys, supernova measurements, and gravitational lensing do not support the notion of an external container or expansion into pre-existing space. Yet, our minds naturally seek tangible analogies, often misinterpreting these abstract signals. By recognizing the limitations of spatial intuition, we can reinterpret observable phenomena correctly. Galaxies recede due to metric expansion, dark energy accelerates distances internally, and the universe evolves without an external reference frame. Our brains may crave a beyond, but the universe doesn't require one. Even more subtly, the human perspective trap emphasizes relativity of position. Every observer, in every galaxy, sees themselves at the center of expansion because space stretches uniformly everywhere. There is no absolute reference point or edge, yet human perception demands one. Understanding that expansion is uniform and intrinsic, independent of any observer's location, is crucial. This realization helps bridge the gap between intuitive, three-dimensional thinking and the abstract, metric-based reality of the cosmos. In essence, the human perspective trap is a reminder that comprehension of the universe requires cognitive flexibility. Spatial intuition, though invaluable in daily life, fails on cosmological scales. Concepts like edges, outsides, and containers do not apply. Expansion is intrinsic, uniform, and internal. To understand the cosmos, we must rely on abstract frameworks, mathematical models, and observational data, letting go of the biases embedded in our evolutionarily honed perception. Recognizing this trap is not just a philosophical exercise, it is a practical necessity for accurately interpreting cosmic expansion and the nature of the universe itself. Current scientific consensus. When attempting to answer the mind-bending question, what is the universe expanding into? It is essential to turn to the current scientific consensus, which provides the clearest, most coherent framework based on decades of observations, theoretical modeling, and rigorous mathematical physics. Across the cosmological community, there is near universal agreement on a few key points. The universe is expanding. This expansion is intrinsic to space itself, and it is not occurring into any external void. The idea that space stretches internally, without requiring a surrounding medium or container, is foundational to modern cosmology and emerges naturally from Einstein's general relativity, supported by a wealth of observational evidence. At the heart of this consensus is the understanding that the universe's expansion is not about galaxies or matter moving into pre-existing space, but about the metric of space itself changing. In other words, the distances between points increase because space itself stretches. This metric expansion is mathematically described by the Friedmann equations, which derive directly from Einstein's field equations in general relativity. These equations link the universe's scale factor, a measure of relative distances at any given time, to its energy content, including ordinary matter, dark matter, radiation, and dark energy. Importantly, the equations make no reference to an external space into which the universe grows. The expansion is an internal property of the cosmos. Galaxies appear to recede from each other according to Hubble's law, not because they are moving through space like cars on a road, but because the very fabric of space between them is stretching. Observational evidence overwhelmingly supports this picture. Hubble's law, first discovered in the 1920s, shows that the velocity at which a galaxy recedes is proportional to its distance from us. This law holds true in every direction and for every galaxy within observational limits, suggesting a uniform expansion without a central point. The cosmic microwave background, CMB, a relic radiation from approximately 380,000 years after the Big Bang, further reinforces the notion of a homogeneous and isotropic universe. The CMB's uniformity and tiny fluctuations provide a snapshot of early cosmic expansion and match predictions from general relativity and inflationary cosmology. Both phenomena indicate that the universe's growth is internal. The space between regions increases over time, but there is no need for an external into to explain this behavior. Dark energy, discovered in the late 1990s through supernova observations, provides additional support for the scientific consensus. Dark energy constitutes roughly 68% of the total energy density of the universe and drives accelerated expansion. Its effects are measurable as the increasing rate of cosmic recession, but again, this acceleration is intrinsic to space itself. No external force is pushing galaxies outward. Instead, the energy density of space generates negative pressure that stretches distances internally. In this context, even as the universe accelerates, it does not expand into anything in a conventional sense. Observers everywhere see galaxies receding faster and faster, but this recession is a reflection of the dynamic geometry of spacetime, not motion into an external void. The topology and geometry of the universe further clarify why the notion of expansion into something external is unnecessary. Observations from the Planck satellite and other cosmological surveys suggest that the universe is extremely close to spatially flat, meaning that on large scales, parallel lines do not converge or diverge. In a flat or even slightly curved universe, expansion does not require boundaries, edges, or a container. Every point moves away from every other point uniformly, maintaining isotropy and homogeneity. Finite yet unbounded models, such as a three-dimensional analog of a hypersphere, also allow expansion without an external medium. In such scenarios, one can travel indefinitely without encountering an edge, and the increase in distances between points is still entirely intrinsic. Cosmologists also emphasize the importance of observational horizons in shaping human intuition. While it may appear that the universe has a boundary, this is merely the observable universe, limited by the finite speed of light and the age of the cosmos. The observable horizon is not a physical edge, it is a limit to what we can see. Beyond it, galaxies exist and space continues, but light from those regions has not yet reached us. The expansion of space carries these distant regions away, sometimes faster than light. Yet this is consistent with general relativity because it is the metric expanding, not matter moving through pre-existing space. Observations of the CMB, galaxy distributions, and large-scale structure all support this understanding. The universe is internally stretching, not growing outward into an external void. Another cornerstone of the scientific consensus is the homogeneity and isotropy principle, often referred to as the cosmological principle. On large scales, the universe appears uniform, with no preferred direction or location. This principle implies that every observer, no matter where in the universe they are, will observe the same general expansion pattern. If the universe were expanding into some external space, one would expect anisotropies, regions moving differently depending on their proximity to the hypothetical outside. Yet observations consistently show uniform expansion, reinforcing the idea that there is no outside. Expansion is intrinsic, isotropic, and self-contained. The mathematical framework of general relativity also provides a clear rationale for this consensus. Einstein's field equations describe how energy and matter influence the curvature of space-time, and by extension, how distances evolve over time. The solutions to these equations, embodied in FLRW cosmologies, demonstrate that an expanding universe does not require a surrounding void. The scale factor, which quantifies expansion, evolves as a function of energy density and cosmic time, independent of any external reference frame. In essence, expansion is a geometrical property of space-time, not a movement into a higher dimensional arena. Even in speculative models involving higher dimensions or multiverses, the observable effects within our universe remain internally driven, reinforcing the scientific consensus. Importantly, the consensus also addresses misconceptions arising from analogies. While balloons and raisin bread are helpful teaching tools, they are only metaphors. Unlike a balloon inflating in a room, the universe does not require external air or a surrounding dough. The analogies work because they illustrate internal stretching, isotropy, and relative recession, but they cannot be taken literally. Cosmologists stress that the expansion of space is metric, not spatial in the classical sense. All physical laws remain local and consistent. Galaxies are carried apart by the changing geometry of space, not propelled outward by an external push. The consensus is also consistent across different epochs of cosmic history. During the early universe, radiation and matter dominated, leading to a decelerating expansion. After a few billion years, dark energy began to dominate, resulting in accelerated expansion. In both cases, the mechanism is internal. The scale factor changes according to the energy content of the universe, and distances between points grow accordingly. At no point does the universe expand into an external space, and all observable consequences, redshift, cosmic microwave background evolution, and galaxy distributions, confirm this internally driven model. Even speculative scenarios, such as the multiverse, bubble universes, or higher dimensional brains, are treated with nuance. While they suggest that other universes might exist in a broader framework, the observable consequences within our universe remain consistent with internal expansion. There is no experimental evidence that our universe is moving outward into a larger space. All measurable effects can be explained by intrinsic stretching of space, driven by its energy content and the laws of general relativity. The scientific consensus holds that, for practical and observational purposes, the universe does not expand into anything. It is space itself that grows. Ultimately, the current scientific consensus is remarkably elegant in its simplicity. The universe's expansion is an intrinsic, self-contained phenomenon. Distances between galaxies increase because space itself stretches. There is no center, no edge, and no outside container. Dark energy accelerates this expansion, but still from within the universe, not by pushing into an external medium. Observations of the cosmic microwave background, galaxy distributions, type Ia supernovae, and large-scale structure all reinforce this view. Even in speculative or higher dimensional theories, the observable expansion of our universe is entirely internal. This consensus reframes the seemingly obvious question, what is the universe expanding into, as a subtle misunderstanding. Expansion is not an outward motion into an external space. It is an internal property of the fabric of space-time, a metric stretching that carries galaxies along and shapes cosmic history. The universe is self-contained, isotropic, and homogeneous. Distances grow, light redshifts, cosmic horizons emerge, but there is no edge to expand into. Modern cosmology teaches us that the universe's expansion is scale intrinsic, an internal growth of space itself, entirely self-consistent and consistent with observation. Closing. After exploring the universe's expansion from every angle, the Big Bang, space-time stretching, dark energy, the infinite cosmos, and the limitations of human intuition, it becomes clear that the original question, what is the universe expanding into, may itself be somewhat misleading. For centuries, humans have tried to envision the universe as a tangible object with boundaries, edges, and a container, naturally prompting curiosity about an outside. But modern cosmology reveals that the universe's expansion is internal, self-contained, and metric-driven. There is no outside to enter, no cosmic void into which galaxies rush. Space itself stretches, carrying all matter, radiation, and energy along for the ride. Every observer sees other galaxies receding, yet no location is special. The The universe expands from within, and in that realization, we confront a profound and humbling truth. The cosmos does not conform to everyday logic, and its mysteries are deeper than our intuition can grasp. Having established that the universe does not expand into anything, we are left with a question perhaps even more perplexing. Why is it expanding at all? The Big Bang provides a starting point, an initial condition where space, time, matter, and energy emerged from an extraordinarily dense, hot state. But it does not explain the underlying cause of expansion. Why did the universe begin to grow instead of remaining static? Could there be fundamental physical principles, as yet undiscovered, that necessitate expansion? Or is expansion simply a contingent feature of the initial conditions at the birth of the cosmos? Cosmologists continue to investigate these questions, exploring ideas from inflationary theory, which proposes a rapid exponential expansion in the earliest moments of the universe, to quantum cosmology, which seeks to unify gravity and quantum mechanics in explaining the universe's origin. Yet, a definitive answer remains elusive. Dark energy compounds the mystery. Observations show that the universe's expansion is not slowing down due to gravity, as once expected, but is accelerating. This accelerated growth, which dominates cosmic evolution in the present epoch, is poorly understood. We know dark energy exists only through its gravitational effects. Its precise nature is unknown, whether it is a cosmological constant, a dynamic field, or something entirely novel. Its presence forces us to confront the possibility that the universe's expansion may be fundamentally linked to aspects of physics that remain hidden, hinting at laws or dimensions of reality that we have yet to perceive. In this light, the mystery of why the universe expands becomes as compelling, or even more so, than the question of what it might expand into. Moreover, pondering the universe's expansion invites philosophical reflection. Expansion is a process unfolding on scales so vast that human intuition falters. It connects the infinitely large with the infinitesimally small, from galactic superclusters separated by billions of light years to quantum fluctuations that may have seeded cosmic structure. Expansion is simultaneously a physical, mathematical, and existential phenomenon. It shapes the observable universe, dictates the evolution of galaxies and stars, and challenges our perception of space, time, and reality itself. In some sense, asking why the universe expands is akin to asking why reality exists as it does, why physical laws permit motion and structure, and why space-time itself has the properties it does. The infinite, self-contained, and internally expanding cosmos also reframes our place within it. Humans are observers of a universe whose growth is uniform, unstoppable, and indifferent to our presence. Our vantage point is constrained by the observable horizon, yet the universe beyond continues to stretch, carrying light and matter beyond our detection. By thinking beyond edges, outsides, and external containers, we begin to appreciate the profound elegance of internal expansion. Every galaxy is receding, every distance is increasing, yet the universe remains coherent, homogeneous, and isotropic. Expansion is not chaos. It is a structured, intrinsic evolution of space-time itself, operating according to deep, universal principles that we are only beginning to comprehend. Finally, the closing wonder challenges us to reframe our curiosity. The question, what is the universe expanding into, has a surprising answer. Nothing external is required. The universe grows internally. But this realization only deepens the mystery. The more we understand about metric expansion, dark energy, cosmic horizons, and the infinite universe, the more we recognize that the ultimate question may not be about spatial growth at all. Perhaps the truer enigma is the origin and mechanism of expansion itself. Why does the fabric of space stretch? What fundamental rules govern this behavior? Could there exist phenomena or dimensions beyond our comprehension that set the stage for expansion? Is expansion an inherent property of space-time, or is it the result of some deeper, hidden law of nature. In the end, the universe challenges our assumptions at every turn. From the Big Bang to dark energy, from the scale factor to cosmic horizons, every piece of evidence reinforces the internal, self-contained, and isotropic nature of expansion. Yet each answer opens new questions. We may never fully comprehend why space itself stretches, why galaxies recede, or why cosmic acceleration dominates the fate of the universe. The universe's expansion is both a scientific fact and a philosophical enigma, a phenomenon that invites awe, humility, and relentless curiosity. Perhaps the most profound takeaway is this: the mystery of the universe is not solved by imagining an outside or a boundary. It is solved, or at least confronted, by recognizing that space, time, and reality itself are dynamic, growing from within, and that their evolution is not constrained by intuition or perception. The universe does not expand into anything. It expands itself. And in this expansion lies a deeper question, one that may forever elude complete comprehension. Why does the universe expand at all? It is this question, more than any other, that keeps cosmologists, physicists, philosophers, and curious minds gazing upward, peering into the depths of space-time, and seeking to unravel the ultimate nature of reality. Perhaps the greatest wonder of all is not the answer, but the pursuit itself, to explore a cosmos that defies edges, exceeds imagination, and grows endlessly from within, leaving us to ponder the why behind the vastness that surrounds us. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.